Earlier this week, the legendary singer-songwriter Gordon Lightfoot passed away at the age of 84. And so today, in Deep Thoughts and something of a tribute to him, I wanted to dig into the real story behind one of his biggest hit songs, The Wreck of the Edmund Fitzgerald. The song details the actual events of a powerful November storm in the Great Lakes and the resulting shipwreck it caused. If you're unfamiliar, the Edmund Fitzgerald was a container ship that sank in Lake Superior in November of 1975. The ship's planned course had it departing from Superior, Wisconsin, across Lake Superior, ending in Whitefish Bay on the opposite side of the lake. But thanks to a powerful late November storm cutting out of the Midwest, it didn't make it. While the forecast did call for rough conditions, the storm ended up being a worst-case scenario for a ship in the position that the Edmund Fitzgerald was in. As the low moved into southern Canada and rapidly deepened, it brought 50-mile-per-hour winds across a long, wide stretch of Lake Superior, maximizing something called fetch, meaning the length of the lake that those winds were over allowed those wave heights to build to incredible heights. Yeah, so while the forecast called for wave heights to be around 8 feet high at the height of the storm, they ended up being anywhere from 15 to 20, estimates even 25-foot-high waves. As the ship was carrying a full load at the time, those tremendous wave heights were just too much for the ship to handle, and it sank, claiming the lives of all 29 crew members on board. Inspired by the events, Gordon Lightfoot released the song you're hearing now less than a year later. He considered it his finest work, and I'd have to agree. That's it for Deep Thoughts here for today. If you have questions for future segments, go ahead and reach out. Send me an email, jim.dickey at abc7.com, and you can always reach out on my Facebook page as well. Has this ever happened to you? A cold, chilly winter morning, you come out into your car, you start up the car, and then on your dashboard, you see that warning light come on. The tire pressure gauge. Your first thought is probably to panic and think maybe you have a flat, which you might. And you should check that. Go around, check your tires, make sure there's not a nail or something in there. There's probably not. More than likely, it is because of how chilly it is outside, like it is, say, this morning. Here at the Dish, temperatures are falling back down into the 40s this morning for the first time in a couple of weeks. Much colder than it was yesterday morning, much colder than it was yesterday afternoon. And that's important. You see, you have to remember what it is that's inside your tires. It's air. It's a gas. And gas is very much affected by the temperature of the air around it. It turns out that the pressure in your tire of the gas in here, the air, is directly proportional to the temperature in the air. So as temperature goes up, the pressure goes up. As temperature goes down, the pressure goes down. Go ahead and take graphics full, guys. There's actually sort of a rule of thumb. For every 10 degrees of temperature that fall, a 10-degree temperature change, you lose 1 psi of air pressure in your tire. And here's why. So inside your tire, there's thousands upon thousands of little air molecules bouncing around, colliding off each other, but also colliding off the walls of the tire. Think of that as the pressure, the number of times you're seeing those collisions of those air molecules with the wall of the tire. When temperatures are up, the molecules are moving around more quickly, more frequently, bouncing off the walls of the tire. But then you drop the temperatures, now the molecules are moving more slowly. You're not getting as many collisions with the walls of the tire, and your pressure is going to drop. Sometimes enough to make that pressure warning light go off. So, what can you do? All you really have to do is go to your local gas station, put a little more air in the tire, and that should be enough to turn that pressure warning light off. And hey, if it didn't happen this morning, it's going to be even colder this weekend, so you might as well do that here in the next couple days. That's it for Deep Thoughts here for today. To give you perspective, I tried to, as close as I possibly could, get these bars to line up with some of those high water marks that were found after Hurricane Ian by the USGS. In Naples, we're talking 6.79 feet of water, so well above my head. Marco Island, we're talking 7+ feet of water. Fort Myers, downtown Fort Myers, the high water mark, 8 feet. Nearly twice my height when you look at this, but still pales in comparison to what they experienced on Sanibel and Fort Myers Beach. In fact, 13 feet plus of water in both spots, too high for our monitors to even really be able to show you. So for that, let's go ahead and zoom it out. Here's what 13 feet of water looks like. To be able to do it, I have to climb this 8-foot ladder, bring out my measuring tape, add an extra 55 inches on top of our tall monitor here in the studio, and there you go. That's what 13+ feet of water looks like. You see that? It's no surprise the damage was what it was in Fort Myers Beach in Sanibel. Take your hands, put them together, and rub them across each other. Think about how, they could get stuck. This is the ground trying to move. So as they try to move past each other, they can sort of get stuck. Tension builds up over time, and eventually that tension releases in the earthquake that was felt. Now, earthquakes are registered on a logarithmic scale by their magnitude. What does that mean? So these numbers go from 0 to 10 in magnitude. The strongest earthquake in Turkey, a 7.8. But it's important to remember, as you go up in each magnitude, you're going up by a factor of 10, and the energy released is even higher. So I want you to think about it this way. Here, follow me over here. We'll do a little experiment. You can actually do this at home to try to understand how the magnitude of these earthquakes work. First, we have a magnitude 5, right? This is a piece of spaghetti. Think about that magnitude 5 and the energy released as snapping that piece of spaghetti. You can sort of feel the vibrations in the spaghetti itself as you do break it. But that was pretty easy to do, right? You go to a magnitude 6, you're upping the energy by a magnitude of 30. So now we have 30 pieces of spaghetti. That is much harder to break, much more energy released. Well, now you go to magnitude 7. Now you're talking about 900 pieces of spaghetti that I would have to try to break to replicate that, which I'm not going to do because I have to keep this for the deep thoughts coming up at 9. And then again, that magnitude 7.8, nearly a magnitude 8, multiply this by a factor of 30. That's the amount of energy that was released in that earthquake from Turkey. So no surprise we're seeing such devastation out of that. Always have your headlights on. This is true even after the sun comes up. Of course, you're going to have your lights on overnight, right? But when that dense fog settles in, of course, it makes it really difficult for you to see. It also makes it very difficult for anyone to see you or your vehicle. You pop those headlights on, it gives other motorists, pedestrians, a much better chance to see you coming, even through the thick fog. Tip number 2, yes, always use your headlights, but you should avoid using your high beams. And that's because, well, when it comes down to it, all fog is these cloud particles, thousands upon thousands of water droplets in the air. When you turn your high beams on, that light is going to hit those cloud particles and then just sort of be reflected right back at you. And that's going to make it even more difficult to see, making matters worse for you as you're trying to get through that fog.